Hello friends. In the last video we have seen the different concepts to improve the efficiency or the network output of the gas turbine power plant or a Brayton cycle. Those are number 1 regeneration, second is intercooling, and third is reheating. Out of that, regeneration and intercooling we have discussed. Now we'll discuss reheating, then we'll do comparative assessment of regeneration and intercooling. Fine. So this part of regeneration, different formulae, and intercooling we have discussed previously. Now we'll come to the reheating. Now first of all, we'll see the schematic diagram of reheating. In this video we'll take reheating, comparative assessment, and we'll go for the numericals. Now if you see in reheating, in the compressor 1 to 2 compression is done, 2 to 3 heat is added in combustion chamber 1, the main combustion chamber. 3 to 4 is expansion in high pressure turbine. Then 4 to 5, this is a reheater. Fine. Reheater, combustion chamber 2 or auxiliary combustion chamber, sometimes it is named as. Then 5 to 6 is expansion process in low pressure turbine. So if you see, the expansion process is 3 to 4 as well as 5 to 6. So work output of the cycle increases 3 to 4 CPT3 minus T4, CPT5 minus T6, addition of these two. Then compressor work is same, but heat addition will be CPT3 minus T2, CP plus CP, T4, T5 minus T4. Now coming to the TS diagram. As we saw in the schematic, what is 1 to 2? It's compression. We are indicating ideal Brayton cycle here. If we consider isentropic efficiency of the compressor and isentropic efficiencies of the turbine, we can draw the actual Brayton cycle too. 1 to 2 is compression. Then 2 to 3 is heat addition. 3 to 4 is expansion in high pressure turbine. Then 4 to 5 is reheating. 5 to 6 is the isentropic expansion in low pressure turbine. Now there are two criteria on which we compare regeneration, intercooling, and reheating. Very first thing, if we talk of the work output, net work output or shaft work of the cycle with reheating, then everybody can see that this is T3, CPT3 minus T4, output of high pressure turbine, output of low pressure turbine is CPT5 minus T6. If you add these two, this addition, as these are diverging on the right hand side, this addition is higher than a single stage expansion. This will have higher value. That means as compared to the Brayton cycle without reheating, single stage expansion, with reheating you have got rise in the network output. So we can say network output or shaft work increases. Reason behind this is turbine work increases for the same compressor work. Let it be with reheating or without reheating, compressor work is same. Got the point? So network output increases. What about thermal efficiency of a cycle? If you think of a thermal efficiency of the cycle, in this case T2 to T3 is heat addition without reheating. If you consider with reheating, additional in second combustion chamber, this is 4 to 5. So this heat addition plus this heat addition, twice the heat is to be added, and this summation is higher. Okay, so more amount of heat is to be added. And if we consider net effect, work output increases, at the same time heat addition increases. What is net effect? Because efficiency, thermal efficiency of the cycle is ratio of net work output divided by heat addition, heat to be added. Okay, so both the things are increased, but there will be comparatively larger amount of heat added, larger degree of rise in the heat addition. That is why the net effect is thermal efficiency of a cycle reduces. That means as compared to the rise in work output, there will be more rise, more amount of heat is to be added in the two combustion chambers. So thermal efficiency of the cycle reduces. Now coming to the optimum pressure, this intermediate pressure, optimum intermediate pressure. What do you mean by optimum intermediate pressure? Optimum pressure is the pressure for maximum output. So this optimum pressure P4 is equal to P5 is square root of this P3 highest pressure into P6 lowest pressure, square root of this product. So this becomes a square root of P3 into P6 square root, which is nothing but P2 P1. So we can write P1 into P2 square root of that. So this is how you can calculate the intermediate pressure. Now what do you mean by this optimum intermediate pressure? As I told you, this is for maximum work output condition. Second thing is, whenever it is mentioned for maximum work output, you require reheating to maximum cycle temperature. That means if this is heated to 750 degrees Celsius, this inlet is at 750 degrees Celsius to the high pressure turbine, you have to reheat to the 750 degrees Celsius. 1200 degrees Celsius, 1200 degrees Celsius. So same, T3 is equal to T5. Then T4 also will be equal to T6. Okay, so this is the thing you have to understand for reheating optimum pressure ratio, intermediate pressure. Okay, now let us proceed further and have at a glance the comparison of all these two. So firstly we'll revise. What is regeneration? This air is compressed, and before supplying to the compressor, it is preheated here, and that is heated with the help of exhaust gases heat from the turbine. So nowhere you are adding burning additional fuel, and you are recovering the heat. So that is why what happens, obviously it will increase the thermal efficiency, increase the thermal efficiency of the cycle. Work output remains same, that is there. This is regeneration. What is, if you plot this on TS diagram, what it will be? 1 to 2 compression, 2 to 3. Now 2 to 3 is actual process. Okay, ideally in regenerator the air is getting actually heated up to 3 only. Ideally it should get heated to the exhaust temperature of the gases, exhaust gas temperature from the turbine. So this becomes ideal temperature T3 dash. So if we get effectiveness of the heat exchanger, it will be actual temperature drop T3 minus T2 divided by, actual temperature drop T3 minus T2 divided by maximum possible temperature drop, that is T3 dash minus T2, or same thing can be written as T3 dash is equal to T5, you can write it as T5 minus T2. So if you see the formula for heat exchanger effectiveness, this is T3 minus T2 upon T5 minus T2. Instead of calling this as T3 dash, we'll call this as T5. Fine, that you have understood clearly. Now if you see the intercooling, in intercooling you have intercooler between the two compressor stages. So here you can see intercooling 1 to 2 is low pressure compression, intercooling high pressure compression. Dotted lines indicate ideal processes and continuous lines indicate the actual processes. Then 4 to 5 heat addition, 5 to 6 expansion, 6 to 1 heat rejection. So 2 stage compression, single stage expansion. Clear? So what happens here, as I told you, here you will be adding, if you have a single stage compression, ideally it will be like this. Actually this will be up to X. That is why in the case for single stage compression without intercooling, lesser amount of heat was required. And here if you go here, more amount of heat is required. What is its effect on thermal efficiency? That will sum up at the end. Then in reheating, if you see single stage compression, heating, and this becomes reheating is there, heating twice, expansion is also twice. So the processes are sum up. You can see this slide and this next one, quite crystal clear comparison of regeneration, intercooling and reheating. So the formulae for regeneration as are written: turbine work minus compressor work upon heat to be supplied. Because of regeneration, instead of T4 minus T2 you have T4 minus T3. That is why lesser amount of heat is to be added. So thermal efficiency of the cycle increases, whereas work output is unaffected, it remains same. If you come to the intercooling, what happens is this is T5 minus T6 turbine work, and due to intercooling, whatever two stage compression is there, this requires lesser work as compared to this single compression. This plus this is lesser as compared to this single stage compression. So the net work output increases, but in that case Cp T5 minus T4, additional amount of heat is to be burned, and net effect is thermal efficiency reduces. If you come to the reheating, then you have output from two turbines, high pressure turbine and low pressure turbine. Single compressor is driving the cycle, divided by heat is to be added twice. So you have got rise in the work. That is why network output increases, and similar to this, network output increases, thermal efficiency of the cycle reduces. Thermal efficiency of the cycle reduces. Okay. Where has it gone? Now, intermediate pressure, I told you, low and high pressure product square root is intermediate pressure for maximum output. In case of intercooling as well as reheating, you get the same formula. This is also termed as perfect intercooling or equal division of work. This is termed as optimum intermediate pressure or reheating to maximum cycle temperature. And explanation, you just can go through what we have seen already along with the basic cycles. So to sum up, what happens with thermal efficiency? In regeneration it increases, and in other two cases, intercooling and reheating, efficiency reduces. Work output in regeneration remains same, whereas work output in case of intercooling and reheating increases. That means if you want to improve thermal efficiency, you will go for regeneration, and if one is expecting work output to increase, not bothered about the efficiency, then they should go for intercooling and reheating. Reduce the compressor work, net work output increases. Increase the turbine work, net work output increases. So that's all about the comparison. Now, coming to the next point, you can have combination of regeneration, intercooling and reheating at a time. All the things are employed at a time. Fine. And the numericals are basically asked on this particular part. Now, just while going through this, you will come to know 1 to 2, 2 to 3 is intercooling. So 1 to 2 single compression, 2 to 3 is intercooling, then high pressure compression, compressor 2. Then if you go further, here preheating will occur from the turbine exhaust. What it will be called? Regenerator or recuperator. So this process becomes 4 to 5 becomes regeneration. Okay, and 5 to 6, what is it? 5 to 6, heat addition in a combustion chamber. So further heat is added in combustion chamber. Got the point? So this is heat recovered. You don't require to add the heat. That is why efficiency of the cycle increases. Lesser amount of heat is to be added. Then 6 to 7 is expansion in turbine 1. Reheating 7 to 8. Then 8 to 9 is expansion in the low pressure turbine. Okay, so compression, intercooling, compression in 2 stages, regeneration, combustion chamber heat addition, high pressure turbine, reheating, low pressure turbine, and then the heat rejection. And ideally this exhaust should get heated to the turbine exhaust. Now this becomes an ideal cycle. If you take into consideration effectiveness of the heat exchanger or regenerator and the isentropic efficiencies of the compressors as well as the turbine, what will happen is you will have to draw actual cycle. The curved lines you will get, this T5 will be slightly lower than this, and then you will have this temperature minus this temperature, or wherever this you have a point, divided by maximum temperature drop, T5 minus this temperature, actual temperature, and this way everywhere the things will change and cycle will look bit complicated, but there is nothing much complicated. We will take one numerical on this combination of regeneration, intercooling and reheating, in which all the concepts will get cleared. Remember, this intermediate pressure again is a product of low and high pressure or initial and final pressure. So P2 in other way, if it is something different, then this formula you have to remember: P2 by P1 is equal to P4 by P3. P2 by P1 is equal to P4 by P3. If you take consider this, P2 is equal to P3, so P2 is equal to P3. If you and P1 into P4, so P2 is equal to P3, that is why it will become P2 square is equal to P1 into P4. So P2 will be under root of P1 into P4, P1, P4, low, high or initial and final square root. Same is the thing about the reheating. P6 by P7 is equal to P8 by P9. 7 and 8 are equal, so that will be square of P7 square, and this will be product of low and high pressure. You will get a square root, you will take a square root, and you will get the intermediate pressure, one and the same thing. Fine. Let us proceed after this for the numericals. Now if I go for numerical. A gas turbine plant operated between 1 bar and 9 bar with minimum and maximum cycle temperature of 25 degrees Celsius and 1250 degrees Celsius. So what is given here? P1 low pressure, P1 or P minimum you can take 1 bar, P maximum, P1 is equal to 1 bar, P2 is equal to 9 bar. Minimum temperature, maximum temperature is T minimum 25 degrees Celsius, 1250 degrees Celsius. The two-stage compressor is provided with perfect intercooling. This you have to understand that there is intercooling and multi-staging is required. Two-stage compressor is used and work is equally divided between the stages. That means intermediate pressure you have to calculate by the formula product of square root of product of lowest and highest pressure, that is 1 bar and 9 bar. Then gases. Here you have got intercooling. Then gases are reheated to 1250 degrees Celsius. Now see, maximum cycle temperature is 1250 degrees Celsius. Heating again to 1250 degrees Celsius after HP turbine. That means heating to maximum cycle temperature. So it is again ideal condition and you will get intermediate pressure as a square root of low pressure and high pressure. Then further this is expanded in LP turbine such that the output is equally divided between two. Fine, again it is one and the same thing for calculating the intermediate pressure. Now calculate cycle efficiency with ideal regeneration. Ideal regeneration means the outlet of this air heated from the regenerator is equal to exhaust gas temperature from the low pressure turbine. And if you see here, friends, assume compressor and turbine efficiencies as 0.83. That means you have to consider actual processes, not ideal one. Okay, so this will become little bit complicated, but if you understand this numerical, you will be able to solve any numerical. The reason behind this is this includes all the cases. Also, this has given what you can see the isentropic efficiencies of the compressor and turbine, so that will make you able to draw the actual cycles, and whatever complicated calculations are you will be able to do. But if you follow certain methodology, particular process, one is bound to understand the concept and easily will be able to solve any numerical. So let us see how to solve it. They have given Cp value, which we take normally 1.005 kJ per kgK, 1 they have asked to assume, and gamma value is equal to 1.4. Let us proceed. So if you see, you will draw TS diagram, two-stage compression, this compression. In this TS diagram you will see 1 to 2 dash ideal process, 1 to 2 actual process. So low pressure compression, intercooling, high pressure compression. Okay, then 4 to 9 is regeneration. Okay, I'll come to this temperature at 9 point later on. Then 9 onwards combustion chamber heat addition. 5 to 6 actual process I am explaining, ideal let it be. T5 to T6 expansion, 6 to 7 reheating, 7 to 8 again expansion. This is in high pressure turbine, this is in low pressure turbine, and 8 to 1 is heat rejection. So this becomes a case of intercooling 2 to 3, reheating 4 to 9, regeneration 4 to 9, and this 5 to 6. 6 to 7 reheating. So intercooling, regeneration, reheating combined. Now as I told you, this is actual exhaust temperature of the turbine. This is equal to outlet temperature of the regenerator. Air will be getting heated to this temperature for ideal regeneration. Actually if they specify, here they have given, see, in this case they have just given the isentropic efficiencies of a compressor and turbine. They haven't specified effectiveness of heat exchanger. If you see the numerical, compressor turbine efficiencies are given. Nowhere they have given this effectiveness of heat exchanger. Would it have been mentioned effectiveness of heat exchanger, they would have given this temperature would have been slightly lower, and from this ideal condition you would have calculated this with the help of effectiveness formula is equal to effectiveness of heat exchanger, let it be 0.7 or 0.75, is equal to this temperature minus this temperature divided by this T9 minus T4, taking T9 equal to T8. Fine, but that complication is avoided. we'll see another numerical in which effectiveness of heat exchanger also is given. Now, given data problem, I have explained you what is the thing. Now, as it is a perfect intercooling, T1 is equal to T3, T2 dash is equal to T4 dash, and T2 is equal to T4. So let us see, this T1 is equal to T3, T2 is equal to T4, T2 dash is equal to T4 dash. Similarly here, maximum cycle temperature reheating is there, reheating to maximum cycle temperature is there. T5 is equal to T7, T6 is equal to T8, T6 dash is equal to T8 dash, and for ideal regeneration, this T9 is equal to T8. So the same thing is mentioned here. Intermediate pressure, already I have explained, product of initial and final, or lowest and highest pressure for reheating as well as what you can say intercooling. Now, what is given thing? Initial pressure is 1 bar, final pressure is 9 bar, temperatures are given as 25 degrees Celsius, 1250 degrees Celsius. So T1 is equal to T3 is equal to this 298 Kelvin, T5 is equal to T7 is equal to this temperature. Now remember, you want to calculate intermediate pressure. You can go this way, or directly you can use formula V2 is equal to P1 into P4, 1 into 9, square root of that, this is 3 bar. This part is already explained, I will avoid repetition. So this becomes 3 bar. Now going further, what you need to do is you want to calculate the intermediate temperatures, because the question is they have asked you to calculate the cycle efficiency. When you want to calculate cycle efficiency, just see the step-by-step procedure or methodology. When you want to calculate cycle efficiency, what is the formula for cycle efficiency? It is work output, net work output divided by heat added. Okay, I'll come to the cycle. What is net work output? It is turbine work minus compressor work divided by heat added is this only, not the whole thing, T5 minus T9. So the formula will be Cp. If you take unit mass, they haven't specified air fuel ratio, they haven't specified mass of the air, so you will take it for unit air flow rate, neglecting mass of the fuel. Excess air is supplied, fuel has to be there, but excess air is supplied, as we saw in the previous numerical, 60:1 or so was the air fuel ratio, so that is neglected. So for unit mass of air, if we consider, we are talking of cycle efficiency. Now this becomes, for cycle efficiency, first of all Wt minus Wc divided by Qs. What is Wt? It is Cp T5 minus T6. Actually you have to take Cp T5 minus T6 plus Cp T7 minus T8 W turbine minus compressor work Cp T4 minus T3 plus Cp T2 minus T1 divided by Qs is equal to Cp T5 minus T9. That's it. Only this thing is required. Now then, what you have to calculate? You have to calculate all these temperatures, because you are given only 1 and 5. So T1 is equal to T3, that temperature, minimum temperature is given. T5 is equal to T7, maximum temperature is given. You are supposed to calculate this T2, T3 you know, T2, then T4, then T6, T8, all these temperatures you have to calculate. Remember, this is the only task. So for doing this, what you have to do, in 2 steps you have to calculate every temperature. For example, if I take this particular temperature, I have to calculate. First of all, I will consider isentropic process, and I will get the relation between temperature ratio with the pressure ratio. So as you know, this will be T2 dash for isentropic compression, T2 dash upon T1 is equal to this P2 upon P1 raised to gamma minus 1 upon gamma. Okay, P2 is intermediate pressure, which is square root of under root of P1 into P4. So P2 value you know. So P2 by P1, P1 was given, P1 is given already as 1 bar. So P2 by P1 is known to you. Gamma is 1.4. So P2 by P1 raised to gamma minus 1 upon gamma is already known to you. Then T2 dash is unknown, divided by T1 is known to you. You will be able to calculate T2 dash. Clear? So ideal temperature everywhere. If you see here, intermediate pressure is calculated. T2 dash upon T1 is equal to P2 by P1 raised to gamma minus 1 upon gamma. So you will get this ideal ideal temperature outlet. Same way you have to get all these ideal temperatures. First of all, I will tell you how to get actual temperature. Then efficiency, isentropic efficiency of the compressor, that concept you will use, that definition you will use. This is, in layman's language, lesser temperature drop divided by higher temperature difference. Lesser difference upon higher, denominator is higher. So if you take this particular thing, isentropic work divided by actual work. Okay, so efficiency of compressor is equal to T2 dash minus T1 upon T2 minus T1. So out of this, T2 you don't know, T2 dash minus T1, T2 dash you just have calculated by the formula. T2 dash upon T1 is equal to P2 by P1 raised to gamma minus 1 upon gamma, by isentropic expansion relation between temperature ratio and pressure ratio. You have got it. So T2 dash you know, T1 already you know, T2 dash minus T1 upon T2 minus T1. Only T2 is known. Efficiency and all other temperatures are known. You easily will be able to calculate T2. Now you have got T2. Let us see. So this way you have got temperature ratio. From temperature ratio you have got the temperature, ideal temperature. Now if you get isentropic efficiencies formula, T2 dash minus T1 upon T2 minus T1, everything is known except T2. You can calculate T2, and that T2 is equal to T4. That is a different part. Got the point? Fine. So coming back to this diagram, T2 you have calculated. Now you know T1 is equal to T3, T2 is equal to T4. No need to calculate T4 separately. Fine. If you recalculate, you will get the same value. Okay. So this is one thing. Then further, if you want this particular thing, 6 and 8 temperatures are equal, any one you can calculate. Okay. So if we will calculate T6, what will happen? T6 or T8, whatever you want to calculate. Again, same thing you have to do. 5 to 6. Say T5 divided by T6 dash is equal to same thing, P5 divided by P6. You just have calculated raised to gamma minus 1 upon gamma. You will get 6 dash. Then efficiency of the turbine will be this T5 minus T6 divided by T5 minus T6 dash. T6 dash just now you have calculated. 5 is already known, maximum cycle temperature. Efficiency of the turbine and all other temperatures are known. You can calculate T6. That's this T6 is equal to T8. Now you know this formula. Okay. Then for ideal, T5 is equal to T7, T6 is equal to T8. Everything is known. Now all the temperatures are known. Now this for ideal regeneration, T9 is equal to T8. What is remaining? Everything is known to you. Now you can. I'll just in a single line I will conclude, and then we'll see the procedure of step-by-step calculation of the solution. If you see, WT efficiency is equal to WT minus WC upon QS. So WT is CP, T7 is known to you, minus T8 is known to you, plus CP T5 minus T6 temperatures are known. This becomes turbine work, minus CP T4 minus T3 is known to you, plus CP T2 minus T1 is known to you, divided by QS. CP T5 was already known, minus T9 is equal to T8. You have calculated. You will be able to calculate thermal efficiency of the cycle. Let us come to step-by-step procedure. Intermediate pressure you have calculated by using isentropic processes. You have calculated T2 dash. Similarly for turbine T6 dash, T3 is equal to T1, T5 is equal to T7. Using the concept of definitions of isentropic efficiencies, you will calculate actual temperature T2, that is equal to T4. Similarly for turbine, you will calculate T6 exit temperature, and that is equal to T8. For ideal regeneration, ignore this mistake. It should be T9 is equal to T8 1181 Kelvin, and then WC is CPT2 minus T1 plus CPT4 minus T3. Substitute the values. Remember here purposely to show you I have did it in this way, otherwise you will come to know T2 is equal to T4 and T1 is equal to T3. So work is same as CP is also same. Okay, so one can wisely write as twice CP T2 minus T1, but just to show you that this is first stage of compression and this is second stage of compression, low pressure compressor and high pressure compressor, both the works are same here. Okay, so twice you can take, or this way also you can do. Similarly for reheating to maximum cycle temperature, you can have same work, twice Cp delta T you can get, or you can do for high pressure turbine and low pressure turbine, substitute the values, you will get this value. Then heat supplied is QCC plus reheating. Sorry, I forgot to add this particular heat. We took, this is regeneration, so lesser amount of heat is to be added, but this part is there, reheating, this is additional thing. So T7 is known, T6 is known, so Cp T7 minus T6, that is to be added to the heat supplied in addition to Cp T5 minus T9, that will be QS. So that one more addition for reheating is to be done, that will give you QS. So Q in combustion chamber plus Q reheating, Cp T5 minus T9 for idle regeneration, which is equal to T8, and Cp T7 minus T6, Cp T7 minus T6, and this is Cp T7 minus T6, you will get, and here you will calculate the value of QS, summation of these two. This you have to remember, combustion chamber, here you have got reduction in heat supply due to regeneration, but reheating requires additional combustion chamber and more amount of heat is to be added here, and net summation you will get, this is QS, and then the efficiency becomes W net upon QS, so WT minus WC upon QS. Just substitute the values from this WT minus WC divided by QS. Substitute the values, you will get this value, and finally you get the efficiency, thermal efficiency of a cycle as 61.25%. Fine. So this is how you have to solve the numerical based on what you can say when the cases of intercooling, regeneration, reheating are combined, and by giving the efficiencies, isentropic efficiencies, etc. We will take few more numericals in which you are given here, if you see this thing, cycle efficiency, work ratio and work per kg of air is to be calculated, and in which we have to get intercooling, reheating, regeneration, everything is there. And here they have mentioned, if you see, heat exchanger effectiveness is also mentioned in addition to isentropic efficiency of compressor and turbine. So this will add more to the complication of the cycle. So this numerical we are going to see, and after that we also will see the case in which there is a pressure drop. We are considering ideal condition that when you go from this to this, constant pressure heat addition is there, but there can be slight pressure drop which we are neglecting. That pressure drop, this pressure drop will be in the combustion chamber and the allied piping. So this will be the pressure drop, and in the regenerator also there can be some pressure drop. So this type of pressure drop numericals also will take. Here we will take all the pressures we can calculate when the pressure drop is given, and from that we can get the required formula used. For example, here if I want, I can use the formula T2 dash by T1, this P2 by P1 raised to gamma minus 1 upon gamma. These pressures are to be used. For this you can't use these two. Previously it was this thing. Now for what is the maximum temperature for this turbine and minimum temperature of this turbine, so this should be known. Then it will become T3 divided by T4 dash is equal to this 5.91 divided by 1.16 raised to gamma minus 1 upon gamma. So these two numericals we'll see in the next session. So for today, or for this particular session, that's all. We'll stop here. Thank you. We'll see other types of numericals in the next video. Thank you very much.